To understand the balance of energy in our atmosphere, we need to talk about what happens with light as it comes into our atmosphere. Yes, visible light does reach the surface, but not all of it. Some of it is scattered and some of it is reflected by the atmosphere. So, we're going to talk about those two topics first before we actually talk about the energy budget. Now, scattering happens when a light wave strikes a small object, such as a molecule or a dust particle or something, and it causes the light to bend. Now, how much the light will bend depends on the wavelength of the light. The longer wavelengths, such as red and orange, are not affected much at all. And so they end up um, essentially moving straight forward. The shorter wavelengths, such as the blues and the purples, are scattered sideways. So the light comes in, hits that molecule, and they scatter off to the side. Now, this is actually quite remarkable because it actually explains why the sky is blue. All right, so imagine you're here at noontime, you're looking at the sun. Well, all the blue light is being scattered away, and all the blues, the violets, and a fair amount of the greens. So the next most intense wavelength is yellow. That's why we see all the reds, oranges, and yellows, and that's why the sun appears yellow, because it's the most intense color of all those wavelengths. But at sunrise or sunset, the sunlight comes through the atmosphere. The purples and the violets and the greens scatter, but it's coming through the atmosphere at an angle, so it has more atmosphere to travel through. So now some of the yellows start to scatter as well. And so pretty soon you're left with oranges and even reds. This is why you often see a red sunset or a red sunrise. It's because all the blues have been scattered to the side, all the greens, and by this point, many of the yellows as well. And there you go. That's just a cool picture of sunset or sunrise where you see the red sun because of the scattering. But there's an additional thing. Imagine you're this person here standing at noon. This light's passing off to the side. That blue light is scattered sideways. Well, where does that blue light go? Right to your eyes. And so what you are seeing, when you are looking at a blue sky, what you are seeing is sunlight that hit those molecules in that part of the sky. The blue light is scattered sideways, comes down and hits you. And so you see blue light everywhere around you. Okay, so that explains why the sky is blue. It also explains why the sun is yellow in the middle of the day, also often red or orange around sunrise or sunset. That's scattering. Now, we also have to talk about reflection, because light very easily bounces off of objects or is reflected. We all have a measurement that we call the albedo. It measures the amount of light that is reflected from a surface. So, for example, here, the Earth and atmosphere, let me actually get a pen here. The Earth and the atmosphere together reflect about 30% of the energy, sunlight, that hits the atmosphere. Sunlight comes down, hits the atmosphere. As it travels, about 30% of that light is reflected back out to space. So the Earth has an albedo of 30. Right? And you can see different albedos. For example, ice has an albedo of 30 to 40. It's a little more reflective. Fresh snow has an albedo of 75 to 95, meaning 75 to 95% of the sunlight that hits it is reflected away. This is why when you go out on a snowy day, it's just absolutely blinding because there's so much light that is being reflected off the surface of the snow. In fact, it's often very common to get sunburned right underneath the eyes in the middle of winter because of all that light that's reflecting off the snow and coming up and hitting you in the face because of the high albedo. Water itself only has an albedo of 10. Grassy fields, somewhere between 10 and 30. The moon, this is an interesting one. The moon only has an albedo of 7. Now I want you to picture you're out in the middle of the night and the moon is full and it is bright, blindingly bright almost. Have you ever seen one of those nights? I've seen quite a few of them. Absolutely spectacular and really cool to see. But the moon only has an albedo of 7. So of all the sunlight that's hitting the surface of the moon, only 7% of it is being reflected toward you on the Earth. That's only 7% of the light that's hitting the surface of the moon. So you can get an idea from that how intense sunlight really is out in space. If you were just out in outer space on the surface of the moon, on the International Space Station, whatever, the intensity of sunlight is just mind-boggling. It is very, very intense. And yeah, it's really cool to think. All right. So in talking about reflection, we need to define this term insolation, not insolation with a U, insolation, S-O-L. Insolation is short for incoming solar radiation. So when we say that the Earth has an albedo of 30, then that means 70% of the insolation coming into the atmosphere is absorbed, and 30% of the insolation is being reflected back out into space. And here's a very basic idea of a budget of energy, a balance. Let's say that we have 100 units of energy, of insolation coming in. Very often, roughly on this particular day in this picture, 6% of that insolation is reflected by the atmosphere itself, 20% is reflected by clouds, and about 4% reflected from the surface of the Earth itself. Add those together, you get a total of 30. Albedo of 30% of our energy is being reflected back out. Well, what happens to the other 70%? Well, it's absorbed either by the atmosphere and the clouds, in this figure about 19%, or it's absorbed at the surface itself. In this figure about 51%, 51 plus 19 gives you 70%. Now, this is a very basic look at the budget of energy, the radiative equilibrium that we have been talking about. But in the next video, we'll dive deeper into the energy budget and see exactly how it works and the role of weather in maintaining that balance.